First of all, thank you very much for this wonderful event. I think it's really important that we discuss long-term security. There is a slight paradox in this title, and it's on purpose. I've had discussions last week with these two people here, and we were talking about dining cryptographers and DCNet, and I think it makes sense actually to make a small distinction between the two. But I'll get to that. Dining cryptographers used to be, in the prehistoric ages of cryptography, used to be a part of folklore. And I know that some people may not know actually the whole dining cryptographer story, so I'm going through that briefly. The idea is that three people are having dinner in a restaurant, and when they have to pay the bill, somebody comes in and says, well, but your bill has already been paid. And now what they want to do, they want to find out if one of them paid the bill or if it was an outsider who paid the bill. And so we have this following setting in which what they do is they're going to, they sit around the table, they use their coins, which will be head and tails, and they will be using their menu cards to shield the view of the coin from one neighbor and show it to the other neighbor. And what typically happens is so that every person will see two coins, and they will say whether the coins are equal or are different. And then what happens is, so this is what happens. He sees their own coin. Everybody sees their own coin, head or tails. Sees the left neighbor coins. So you can see these are the left neighbors. They're going to compare, and so they're going to say different or equal. But there is one extra rule. The person who paid, he will lie. Well, he will invert his statement. He's following the protocol, so he's not lying. But he will invert the statement. And so they're going to say out loud what they see. And the result is actually as follows. In this specific case, the parity of difference is 3. 3 is an odd number. And so that means that one of them inverted their statement and one of them paid. So if you, and about the privacy, so in this case it was P3 who paid. Now, for instance, if you go into sit into position of P1, P1 cannot decide whether it was P2 or P3 who paid, because there will always be a coin flip that he does not know, and either outcome will be consistent with one of the parties paying. And the same holds for P2 in this case. So here I'm repeating the protocol. Maybe the most important part is that I generalize the protocol. So what is the rule of the decision? Well, if the parity of difference is even, then nobody inverted, and if the parity of D is odd, then one of them inverted and paid. So this is the fundamental, the basic dining cryptographers protocol. Now it's rather trivial to switch it from coins and different and equals. You can use just zeros and ones, and you use the modulo 2 sum. So this is how the protocol would look in that case. So what actually is happening is that the people, they will announce their Y1, Y2, and Y3. And if you trace down the randomness, what happens is that like this R1 appears also in this case. And so all the randomness cancels. And so what is revealed essentially in modulo 2 is the sum of Y1, Y2, and Y3. So this was the discussion we had last week. What is the functionality that's actually we implemented? And we consulted Wikipedia, and it said that the secure multi-party computation of the Boolean OR function. And even there's a paper by Tapp and Anne Bodman. They also call it anonymous veto. However, this is the setting of the dining cryptographers, but this is not actually what Schaum is implementing. What Schaum is implementing is he's computing the exclusive OR of the inputs. So this is different. And essentially, if you look in the context of anonymous broadcast, then this is the kind of functionality that we want to generalize and that we want to use. So it's very easy to see how to generalize it for strings of arbitrary size. Here I choose the size is 8, and so what they do, they just repeat it and do the exclusive OR bitwise. And again, all the randomness cancels. And you can also generalize the algebraic operation. And the only thing that you must take care of is now that if you use the modulo 2, addition and subtraction is the same thing, but now you have to really make sure that people subtract. And I didn't mention that, but you can generalize this to also more participants. So the way I try to think of it is that the first part is what I will call dining cryptographers, but now we're going to work on these CNETs. So we're going to take the basic dining cryptographers protocol and try to implement anonymous message broadcast. And so the idea is that what we want to accomplish is sender anonymity or message unlinkability. So people would, you think of Twitter. You want to have a Twitter service in which people can have short messages, but it's completely anonymous. So why want we to do it? Well, we want to do this, for instance, for voting or for other reasons, for privacy reasons. So here, one of the things that we can do now is we can repeat the protocol sequentially, I would say in the same transmission. And we call all these, from now on, we call this slots. So the users, so all the randomness is already resolved. What people will do, they will choose a slot and they will occupy a specific slot. Here we have 12 slots, 8 people. Nevertheless, the chances are high that we will have collision. So this is the famous collision problem of dining cryptographers. Yet another problem that may occur is that people may deviate from the protocol and therefore disrupt communication. I will say very little about this in this specific talk, but okay. So one of the first approaches that I worked on with my co-authors over there is to have parallel repetition. So what we do is that, well, we have what I will call a channel, channel 1, channel 2, channel 3. Every party chooses randomly in each of these channels. And so you hope that at least in one channel, the message will go through without any collision. So you have success. I will call a message successful if at least in one channel there is no collision. Well, and so I'm not going to much of the details of it, but the paper has the whole analysis, like I will call lowercase k is the number of parallel channels that you need, given a certain amount of slots, total amount of slots. You want to find the k that maximizes the probability that all messages are successful. And another thing that we analyzed is if you allow some error probability, then what is the number of slots that you need given the number of participants? What I just like to show you this is the birthday paradox. Instead of 365, it's using 360. So the first line is actually the birthday paradox for one parallel channel. So that's the original birthday paradox. And what you see here is that if you have 10 parallel channels, each of size 36, so the overall size is again 360, then you can get to a very high chance that your message will get through. This is just to get a feeling of what this approach can give us. I skipped this. The combinatorial analysis of this is very complicated. It's not easy. And to the extent also that we had to make approximations for the higher value using Poisson distribution, and then we tested the theoretical results with the experimental results we had. Okay, I'm going to skip this. So now I'm going to present some very fresh ideas. Most of them are less than 3 months old. The first idea is actually a continuation of what you just saw. What parties are going to do, they're going to send multiple copies of their message, but inside the message as metadata, they will include the slot numbers in which all their messages are. Now, what is the advantage of that? That is, if one message is successful, if I have, like, I'm in slot 3 and it's successful, I may have a copy that's in slot 8, which is in a collision. But now I can subtract that collision from that specific slot, so I can reduce the number of collisions in the other slots. And so this is depicted in this example. Here we have 5 participants, we have 9 slots, and each participant chooses 3 slots. And so what we have now, for instance, is that in slot 5, message 4 is single. I want to make this short. So what you see here is, this is actually what the people will see. They will see, you can make a collision counter. That's not difficult to do. By using a modulus that's bigger than 2, you can count the number of collisions. So the bottom line is what the people will see, and the upper line is like sort of God's point of view. He can see everything, and that is good enough to simulate this. So here, this is message 1. Now message 1, we know what the message is, so we can subtract it. The value of this message, we can subtract it from slot 2, so the number of collisions there will reduce to 2. And then if you're going like that, you get the idea? Is it okay? What you can do is you can see which messages are successful, and you can simplify the collisions, and then at the end, everybody's message gets through. So this is the first idea. And it is hard to, I'm still not very hopeful of being able to analyze this combinatorially, but I did some preliminary simulations of it. Because it's very obvious, if you add the number of slots, then the collision probability will reduce. So in this specific case, we have, after 10,000 tests, where n equals 20 and k equals 60, then no failure occurred. So this is very good, because it's like we're paying a factor of 3 to have almost no collisions. Whereas in the other example, the birthday paradox example, it was like a factor of 15. So now we have, what we are paying to have no collisions is a factor of 3. So this is preliminary work. I still have to, I want to do very extensive tests, test 1 million tries without a failure, and then I would say, okay, this value is secure. So this is the first approach. The second approach is based on fountain codes. In this case, people will just occupy a slot, let's say, with probability 50-50. And we will do the arithmetic in this example over F2. And well, what happens is this. So what we're going to, if you invert the matrix, so now the slots are on the right, and the participants are I mean, the slots are the rows and the participants are the columns. Now what we have is we have a system of equations. So the O's are the outputs of the Dining Cryptographers channel. People will randomly choose to participate in some of the slots. Now the question is, so now we have m equations with n equations with n unknowns over F2. Now if m equals n, then we know that there is a solution with a probability of about 30%. This is a well-known fact about random matrices. Now what we're going to do, we're going to add a little bit of equations, and so we make the chance that there will be, that it's not possible to solve the system will drop exponentially as you add the number of equations. So this can be proven. And so what we have, if I have an n by k matrix where k is like maybe 30 more equations than we have unknowns, then the probability that you cannot find the solution is less than 1 in a million, in a billion. So the problem is that in this specific case, you need to, the parties need to communicate the positions that they have been using. And this has to be done anonymously. So you must need the previous method to communicate these positions. From that point on, you can use this method inspired on fountain codes. So what we see here is that the overhead, what I call the overhead, is getting close to 1. Now, the final question is, can we get to 1 exactly? Because we know that we need n slots to send n messages. And the answer is yes, we can do that. In this case, I'm using a finite field which is not binary. And what every party does, it will compute the message, the square of the message, the cube of the message, all the powers of the message. And so if you look at what the DC channel does, then the channel, this will be the first slot, the sum of all the messages, then the sum of all the squares of all the messages, the sum of all the cubes of all the message. The final one will be the sum of the n power of the message. And these values will, the p's will be made public, and the question is how to recover then the messages m1, m2, up to mn from this. Now this is very funny. I thought about this for a long time, but this is a problem that goes back to Newton and even to Jeroen. It's like 350 years old problem. What I'm going to do, I'm going to give you a very simple example where n equals 4. What you do is the following. So suppose you define this polynomial, m1, m2, m3, m4, which obviously has root m1, m2, m3, and m4. Then if you write it out like that with the s's as the coefficients, and you compare the degrees, this is what you get. And what's called the Newton identities, and you even can find them on Wikipedia, is that from the p's that we had on these transparencies, there exists very efficient recursion relationship that will compute the s's like that. So this would give us the following procedure for solving the collisions. Each party will send the vector of m. The DC net will do the addition. Then you use the Newton's identities to compute the values of S, and then you have to factor F over a finite field. And this in my vision, I'm thinking of DC nets that will have a few hundred users, and for a few hundred users, factoring polynomials of this size is very doable. I even did some tests with Sage, and up to 500 factoring polynomials is not a big deal. So yeah, as I said, factoring is not a bottleneck. However, the method does not work smoothly over binary fields, because in binary fields what happens is that 2 equals 0 and all odd numbers equal 1, and that means that all these equations will disappear, and this will be a 1, and the recurrence relation doesn't work very nicely. I've looked at it for a day and I've not been able to solve it, but I'm not going to worry about this for now. And the other observation is that, well, you don't want to use this method maybe for very long messages. I don't know, if you have a message of each message several kilobytes or so, maybe you don't want to use this, because then you would either have to do it in chunks and do the factoring for each chunk, or you would have to do it over a very large finite field. So there are some trade-offs, and actually there's another trade-off that I didn't mention so far, because I've cheated you. I have supposed so far that all the parties are honest, but we want to catch parties that are not honest. And the way we are going to do that is we want to use proof of knowledge. They have to commit to the randomness, and they have, in each and every step, they have to prove that what they are doing is consistent with what they are supposed to do. And so actually, the computational cost of this proof of knowledge should also be incorporated in the whole accounting. And so it may very well be that, for instance, the last method is algebraically, I think it's very elegant. There's nothing better that you can expect. But in practice, it may actually not be the most efficient thing to do. Which brings me to the practical part. I have a strong vision that I want to make DCNets practical. And when I say with DCNet, I think of a peer-to-peer service in which there are no special roles. I don't like it when you have authorities or I don't know what. I would like everybody to be equal, even though in this case it may be helpful to have a bulletin board, but everybody could be a bulletin board. I'm thinking of Twitter-sized messages. The commitments to be used will probably be Peterson commitments, though I have become now enthusiastic about of Olivier's commitments using the pairing thing. Maybe they have more properties. I envision a service, because this is another thing. Often, well, not in the practical papers they're out, but in the theoretical papers there are people have like, it's one Dining Cryptographers protocol. It's like there's nothing before, nothing afterwards, it's just one protocol. Whereas I'm thinking of something that's continuously in the air, and like every minute or every 5 minutes there will be a new output and a new batch, and you can have overlapping rounds and sort of pipelining of rounds. I think this is something I want to look in the future. People should be able to easily opt in or out, and we also need to deal with resilience. I had discussions with Julia about this, about including secret sharing in the whole process. So the plan for me is now to study the existing systems. These are, I think, the main systems that are around. I was hoping that the people from Yale would be there. I don't think he had time to.
Representative of one of Brian's.
Brian, right?
So yeah.
Okay. So there's one thing I would like to point out about the third solution, in which Christian Frank has been working, and I've been later on talking to him as well. That's a different setting, because in the setting that I just proposed, it's like you have n participants, and each of them will send a message of the same size. And what's completely different in the other setting is that there is no probability distribution on the messages that you get. You have a collision, and as you get the collision, you start a collision resolution protocol. So the difference is, in that specific case, you do have feedback all the time. Whereas in the case that I just presented, it's like one shot. Everybody uses n slots, and then you get the result. So it's a different setting. My feeling at this specific moment in time is that maybe the most fertile thing to do would be to combine the two settings. I just want to end. This is the last slide. I had another discussion some time ago, 10 years ago, with somebody about voting, and this was based on private channels. And then this person said, yeah, but private channels don't exist. Now that is true, but we can emulate a private channel in various ways. And I think people should have the choice to implement a private channel the way they want. They can use quantum key distribution. They could exchange a terabyte hard disk. They could use like post-quantum public key cryptography, McLeese and AES, or the new post-quantum key exchange protocols that are around there. I think this is what my criticism on sorry for the Yale people, but the criticism I had is that it's not unconditionally secure, because the key exchange and everything is based on Diffie-Hellman, on elliptic curves, and this is computational. So I don't think it's nice. I mean, it's practical, but I don't think it's nice to have a Dining Cryptographers protocol which is originally unconditionally secure, and then sort of, to make it efficient, downgrade it to something that's computationally secure, which, by the way, is more Golodjuel's choice than the people from Verdict in Dissent. That's my talk. Thank you.